Well, thank you so much. I'm glad to be here again. My name is Sebastian Passanante, and today I'm going to tell you about how we can synthesize magnetic nanoparticles inside a mesoporous thin film. So let me change. Okay. So first, what is a mesoporous material? As the name indicates, they are porous material with a pore size between 2 to 20 nanometers. These pores, of course, they can be filled with different species. In particular, we are interested in fill them with nanoparticles. In the literature, there is a great advance and is well known how you can synthesize metallic nanoparticles, but of single elements like gold, silver, or copper. We are interested in synthesize inside these pores a more complex material, complex in the sense that we have more than one element. So the question that we are looking is how can we incorporate complex oxide nanoparticles inside this mesostructure? In particular, we want to incorporate nanoparticles of the manganite lanthanum strontium, the LSMO. We are interested in this manganite because it presents ionic conduction and magnetocaryotic effect. Here I bring you some, I have the, here's the pointer. I bring you some image. The first is for scanning electron microscope. As you can see the surface of the thin film that we are working now. This is a silicon dioxide mesoporous. And in this TEM image, you can see the distribution of the pores better. In our case, we are working with a pore diameter of 8 nanometers. So how can we put these nanoparticles inside the mesoporous matrix? The strategy that we take is by pulse laser deposition, PLD. This technique is thinking for growing thin film layers. But in our case, we have a mesoporous thin layer. So the LSMO, when you grow it, have two different possibilities to grow. On the surface, like a thin film, and inside the mesoporous matrix. As a thin layer, it's easy to observe. As an example here, in this same image, you can see the LSMO layer. But what is happening inside the pores is the difficult question. So the next question in this talk is, what we're gonna want to answer is there manganite inside the pores? So for that, we grow a series of samples. The first are the meso samples. We call meso because they are growing on a mesoporous thin film. The number here indicates the nominal thickness of the sample. We grow with 5, 20, and 100 nanometers. And dense samples, because they are growing on a dense silicon dioxide. These samples function like a control sample to a better comparison with the meso one. So if we look at the surface of the samples by scanning electron microscope, for meso 100, we have a polycrystalline growth. This growth is very similar as the one you have in the dense sample. If we pass to meso 20, the polycrystalline growth is still here, but for meso 5, we can see any grain. So this is showing that part of the manganite may be inside the pore. As you can see here, this fingerprint pattern is very similar at the one that I showed earlier in the silicon dioxide layer mesoporous at the first of the talk. And if we measure the accessible porosity by X-ray reflectometry, we can find that 38% of these pores are empty and they are available to be filled. If we do the same for meso 5, we found that 27% of that accessible porosity is filled, let's say now, with something. So for knowing what is inside the mesoporous, we have done transmission electron microscope, some image. I bring you here an image for meso 20. As you can see, here is the manganite layer, the mesoporous layer, and the dense layer. As you can see here, there is a change in the density for the meso layer, as one expected. And what we did here is mapping lanthanum by yields. The results are here. We see a strong contribution for here for the LSMO layer, as we expected. Here is lanthanum, but there is a weak signal, as you can see here in a very little lume. This is showing that lanthanum is in the pore. So the next question is, lanthanum is in the pore. Is this ferromagnetic as is the LSMO? So for that, we did a series of magnetic measurements. Here you can see the magnetization against the temperature. We found that all the 6 samples present a paramagnetic to ferromagnetic transition. And the next I want to highlight is the Curie temperature. For the fecal samples, meso 100 and dense 100, the Curie temperature is the same for both. But when we decrease the thickness, so we are getting more important what is happening in the pores than what is growing as a thin film, we can see that the Curie temperature is completely different between the same samples. As for example, for meso 5 and dense 5, the TC are 200 away one from the other. And in particular, the TC that we have for meso 5 is the same as we have in bulk. Next, the hysteresis curve show a ferromagnetic behavior for the 6 sample, and we have found that the coercive field is greater for the meso sample. So the mesoporous layer is playing a role in this way, is increasing the coercive field. Next, we found that the meso 5 needs larger magnetic fields to get saturated. So this is a different behavior than the other samples. And we also found that the saturation is larger for meso samples than the dense. And finally, I bring you here, if you want to interpret it, if you have magnetic nanoparticles here, you maybe compare field cool warming and zero field cool curves. In the dense case, as you can see here on the left, there is no difference between the 2 curves or a little curve like here. But for the meso sample, as you can see here, the difference is very clear. And this difference is increasing while you decrease the thickness. In special, meso 5 shows a larger difference. This is the sample when the contribution from the meso layer is more important. And the conclusion here is that we have magnetic nanoparticles, but with weak interaction. It's interesting that these weak interactions can be tuned in next works that we have to complete by changing the pore size. So finally, as a conclusion of this work, it is possible to grow the LSMO inside the pores of the silicon dioxide mesoporous layer by PLD. The Curie temperature is different from meso and dense samples. In special, meso 5 have a Curie temperatures that coincide with bulk. And the zero field curve shows that the presence of magnetic nanoparticles with weak interaction. And finally, this work opens the possibility to incorporate magnetic nanoparticles of complex oxide inside mesoporous material. So thank you for your attention, and if you have a question, I'm here.
All right, thank you, Sebastian. Please raise your hand if you have any questions, or you can also use the chat box.
All was clear, all was simple.
Sebastian, I have a quick question. So when you are talking about the LCMO, so do you aim for like anisotropy?
Isotropic in what sense?
Like you do a top layer I have seen as a LCMO. So do you like aim for like a amorphous crystal structure, or you aim for, because I have seen
No,
some
we
groups.
aim for something crystalline.
Okay.
We can see now in TEM, we did this measure, but it's very difficult to see because the amorphous layer of the mesoporous is amorphous. So it's very difficult to see the crystalline size, but we think that it's crystalline because the ELSMO to be magnetic need to be in a perovskite structure.
Thank you. All right. I don't see any other questions, so we can thank the speaker and move to the next one. All right. Thank you.